Hello, everyone. I am Andrea. I'm a PhD student at the University of Groningen, working with Filippo Fraternali, and I will graduate at the end of this year. So with this talk, I would like to show you what I have done throughout my PhD, which has been in particular on the study of these gas flows from and through galaxies. So the general topic of my research and what I've done in these years is the study of these dynamics and the origin of this cool 10 to the 4 Kelvin gas that we observe in the halos of galaxies. And this, I believe, is very important, that anybody at this meeting would agree that is crucial to understand what is the evolution of galaxies, how do galaxies form and evolve. So in particular, I'm trying to understand whether this cartoon, the picture depicted in this cartoon, is correct or not. So how is this gas moving in the halos of galaxies? So I've done this using semi-analytic parametric models that I developed and comparing the predictions of these models with real observational data using the observations of different samples of galaxies. And I've done this using a Bayesian analysis, and the results of this analysis helped me in carrying out some interesting, I think, insights on the nature and different properties of this cool circumgalactic medium. Here I'm showing already what are the results, the main results that I have achieved, and all this work has been done in collaboration with Filippo Fraternali and Gabriele Pezzulli. And I'm going to talk about 3 main works that we developed together. And the first one is on the cool CG, the study of the cool circumgalactic medium in early type galaxies. The second one, the study of this cool gas around star-forming galaxies. And the last project that I'm still carrying on is on the cool circumgalactic medium around our closest neighbor, which is M31, the Andromeda galaxy. Okay, so the first project that I had was the study of the CGM around massive galaxies, and all the results that I obtained, that we obtained, are published in this paper from a couple of years ago. So you can find here any more detail if you're interested. And so the key question that we had here was trying to understand what is the origin and fate of this large amount of cool gas that is present, that is observed in the halos of very passive galaxies. We can see that here in this example, these are the observations from the Halos survey, and you see how the amount of neutral hydrogen observed, the column density observed in the halos of passive galaxies, is more or less the same that is observed also in star-forming galaxies. So we want to understand how is this gas not actually feeding the star formation of the passive galaxies that we are interested in. And also we try to do this, trying to investigate the kinematics of this gas. So the kinematics that is observed for this medium in early type galaxies is very peculiar, because these clouds have very low velocities, and indeed the velocity distribution that you can see here is very narrow with respect to the expectations, and the velocity dispersion of this distribution is only 0.6 or less the virial velocity dispersion for these very massive objects. Okay, so we had tried to investigate this problem using our models, using my semi-analytic parametric models, and here I tried to model a virial halo of about 10 to the 13 solar masses, and I assume that this gas is formed by clouds that are falling down towards the center, and their motion is driven not only by the gravitational force, but also by all the interactions with the hot corona. And then I compare these predictions from my models with a sample of 16 luminous red galaxies that I took from the COS-LRG, from the data of the COS-LRG collaboration. And these galaxies have masses that are indeed of about 10 to the 13. The halos are indeed of about 10 to the 13 solar masses. Okay, so I've done this comparison using Bayesian models, and these are the results of this analysis. So what we have found is that the accretion, the amount of accretion that is reported in the data is consistent with the cosmological accretion, where by cosmological accretion I mean the fractioning gas of the dark matter accretion that is predicted for this kind of halos by cosmological models. And then these clouds need to start at the virial radius with very low velocities and with masses of about 10 to the 5 solar masses. But then, while they fall down towards the galaxy, they need, in order to reproduce the observations, they need to evaporate in about 500 mega a year, so half a giga a year. And we can see how you can see how the predictions of the models that are shown here in blue actually reproduce very well the observations of the COS-LRG survey. So here I'm showing the kinematics, and you see how our predicted distribution is very narrow as in the observations. And the velocities are low because these clouds are actually slowed down by the interactions with the hot gas. So you see how the clouds, one cloud, here I'm showing the velocity of the cloud with respect to the distance from the center. So these clouds start at the virial radius with a very low velocity, but then instead of being accelerated only by the gravitational force, as in the ballistic models, is slowed down by all the interactions with the hot corona, mainly the drag force. And not only is slowed down, but also these clouds are destroyed by the interactions with the corona. So we start with a mass of about 10 to the 5 solar masses, and then one single cloud actually loses its mass, and after 500 mega years or so is completely evaporated into the hot corona. And this means that most of this gas is just evaporating into the hot medium and is not accreting in the galaxy, is not feeding the central galaxy that is indeed passive and not forming stars at the moment. So these are the two main results that we obtained with this first work. So we have that we can reproduce with inflow models the kinematics, at least, of the observations of this gas in luminous red galaxies, and also that these clouds are evaporating into the hot corona and are not feeding the central galaxy. Now, the second work that we performed, that I have done, is the study of the cool circumgalactic medium in star-forming galaxies, and these have been published just a few months ago in this paper. And I've also posted a video and new results about this, so I'm not going to go into many details here, but you can, if you're interested, you can go and look at the video or, of course, at the paper. And what we have done here is trying to model the medium, this cool medium around the star-forming galaxies with models of wind. So these clouds are ejected by the center, and these winds are powered by the supernova explosions in the disk. And we have compared our predictions with around 40 galaxies from the COS halos and COS gas collaborations. And what we found is that to reproduce the observations, we need the efficiency of the supernovae. So, I mean, the efficiency of the supernovae in transferring energy to these winds of about 250%. And this is clearly unphysical. So our first conclusion is that we need unphysical energy requirements for these winds in order to reproduce the observations. And therefore, we can conclude that supernova-driven galactic winds actually do not reproduce at least most of the cool circumgalactic medium in the halos of star-forming galaxies. Now, what I want to talk about in the second part, last part of this talk, is what I've done in the last few months, and these are the results. These are very recent results that I hope will be published soon. And I'm trying to apply my models to a relatively new set of observations from the AMIGA project on the cool circumgalactic medium of M31 of the Andromeda Galaxy. And in this case, they have around 40 line of sights going from the center to 500 more or less 500 kiloparsec from the center of M31. And these line of sights are spanning the entire halo of Andromeda. And this is very interesting because normally we just have one line of sight per galaxy, but in this case we have lines of sight spanning the entire halo, so we have many more spatial information on the distribution of this gas. Here I'm showing the observations that we have used for this work, and in particular we selected only the lines of sight that are within or just outside the virial radius. So on the left, you see the kinematics observed for this gas. And when you see more than one circle on top of each other, that means that there are more than one kinematic component for that line of sight. And on the right, we see the total silicon column density that is observed, that is derived for this gas. And having this information about the silicon column density is very important, because with our models, we can predict what is the total gas column density in these predicted by our models. And just with the comparison of this column density with the silicon information that we have, we can estimate, without using any photoionization models, the metallicity of this gas, which is a very important property, of course. So what I've done is try to apply my models to this data, and I find that winds, as for the other star-forming galaxies, are not a good way to reproduce this medium, because we need, again, supernova efficiencies that are unphysical, of the order now of 300%. So we conclude that these winds model are not a viable way to reproduce the cool synchrogalactic medium. But then I've also tried to apply inflow models. So models in which, as for the first paper, these clouds are inflowing down towards the center, accreted at a rate that is consistent with the cosmological one. And with these models, we can successfully reproduce observations. And you see it here in these plots. So in the top, we have the number of kinematic components. Then we have the total silicon column density and the kinematics, so the velocity of these clouds with respect to the systemic velocity of M31. All of these properties are as a function of the projected distance from the center. And the observations are shown as points, while the different bands, so these two bands and this color map, represent the prediction from our models. And you see how our models are successfully reproducing the observations, except for a few outliers in the kinematics and in the column density. And we are just under-reproducing slightly the number of components, but we are still within the errors. So in order to reproduce, to have these predictions, we perform I performed the Bayesian analysis. So these are the best models with the best choice of parameters to reproduce the observations. And this is the result that we had from our Bayesian analysis. So these are all the parameters, the physical properties that we need for this inflow of gas to reproduce these observations. I'm not going to go into the details of all of them. I just want to stress that we were able to estimate the metallicity, which was a free parameter initially, and we estimate that in order to reproduce observations, the metallicity should be very low, lower than 0.1 solar. So this comes up in a very self-consistent picture in which we have low metallicity gas that is accreted from the external regions and is going towards the center and is reproducing the observations of the AMIGA projects. Okay, so here you see all the conclusions of these three works. So we have found that for early type galaxies, the clouds are inflowing towards the center and are eventually destroyed by the interactions with the hot corona. That in star-forming galaxies, the cool circumgalactic medium cannot be produced by winds, by supernova-driven winds. And that in M31, we seem to have a very self-consistent picture in which this gas is accreted by the external regions and has a very low metallicity. Now, in the last minute or so, I would just like to tell you what are the future perspectives for this kind of models. And the first one being, of course, the interplay of these models with high resolution hydro simulations, which is something that I plan to do just in the next future, in the next months. And we can, so I can apply the prediction of these models to two hydrodynamical simulations to have initial conditions for these simulations, like the mass of the clouds or the initial velocity of these clouds. And then from the results of these simulations, I can actually refine my models, in particularly looking at the interactions between the clouds and the hot phase. And within using this interplay, I can actually improve also the comparison between model predictions and observations. And the second very important application is, of course, using these models to try to interpret a new set of data. And there are a lot of examples already out in the literature of data that I can use that I can apply my models to. And there are also, I've listed some of them here, but there are many more. And I hope I've convinced you that with this kind of models, we can actually gain a lot of new insights on the properties of this cool circumgalactic medium. And yeah, so this is all I wanted to tell you. So thank you very much for your attention. And if you have any questions, I'm very happy to talk about anything that I've discussed in the last 15 minutes. So feel free to send me an email or a message on Slack. Thank you very much.